Hello, I'm Jane Berry. I've been working with signal integrity for over 30 years. Most recently, I've been working on some features in eCADStar. And over those years, nothing stood still. The hardware has changed, and the whole philosophy has changed. As in other parts of technology, signal integrity is not just a thing in itself, you have to see it in context. So in this short series of movies, I'm going to do just that, to show some typical things you might consider, starting with the schematic, through to final PCB design, to achieve a good, robust signal integrity.
For signal integrity, we're mainly thinking about high-speed digital signals, and often that isn't all the signals in a PCB design. Dividing a design up by schematic sheets and adding some descriptions makes that a whole lot easier. Let's look at the DDR4 memory circuit. It's controlled by an FPGA by connecting to multiple I/O banks. These are the data lanes, and this I/O bank is connected to clock and address command and control. Over on another schematic sheet are the DDR4 SDRAMs themselves, with all their connections to power and their data, command, control and clock connections. If we wished, we can make these into reusable hierarchy circuit blocks, avoiding redesign in the future. We can simulate to check some assumptions before we commit anything to physical design. How about this DDR4 clock? Have we selected the right differential impedance? Have we picked the right drivers at the controller end? We select the clock signal on the schematic and create a scenario. The scenario is a high-speed equivalent circuit that includes the connectivity and the schematic. We can edit that equivalent circuit to represent our intentions when it comes to physical design. To check out our proposed topology, we have to make sure the transmission lines represent the correct layer stack and that the buffers represent the right kinds of simulation models. We browse available IBIS simulation models and import them into our local simulation library. And after that, we can assign them to the buffers in our scenario. We can assign models that include the package parasitics, or we can just model the silicon itself. First, we assign a model to the driver, and then to all of the receivers. Next, the differential transmission lines. Firstly, we have to make sure their lengths represent the intended route lengths in the physical design. In this case, that's 14 mm. And the transmission line parameters have to represent the correct track widths, track spacings, and layer stack. We can edit the track cross sections and solve using a field solver to get the transmission line parameters. In this case, we're aiming for a differential impedance of about 85 ohms. Now we've solved the track cross-section, the updated transmission line values appear on the symbol. Now we've edited the scenario so it's a good match for what we're going to put on the PCB, we can simulate. In this case, we're just going to set a stimulus of periodic pulses, but there's also 8-10-bit encoding and all sorts of other options, including customizing the whole thing. We've simulated an eye pattern. You can see that there's a pretty decent opening here, and for this demonstration I'm not going to go any deeper than that, but you can do current waveforms and stimulus waveforms, test load waveforms, and frequency domain analysis and all that good stuff as well. Okay, some questions tend to arise from all this. Can you save scenarios so that you can compare results when you get to physical design? Well, the short answer to that is yes, and the long answer is yes and then some. When you get to physical design, you want to compare the results to make sure that what you intended is what you got. All the simulation models the scenario used are saved with it. And scenarios and simulation look and feel exactly the same when you get to PCB design, because they are exactly the same. Why do you have to set simulation models in the scenario instead of in the design itself? Well, you absolutely can set simulation models directly on the components themselves. That keeps them with the design data, and it makes them available to all scenarios. So it's a useful thing to do. But a scenario is what it says. It's something you might do. It's a what-if scratchpad. And so not only can you see right in front of you exactly what you're going to simulate, you can ask questions like, should I use 8 milliamp drivers here, or would 6 milliamp drivers still perform fine, and then get the power consumption down? Can you model shielding and coupling? Yes, you certainly can. The difference between simulating coupling here and in physical design is that in physical design you can extract the coupling, but here the coupling isn't known yet, so you have to edit it into a scenario. Say for example you wanted to simulate coupling between adjacently routed bits of a byte lane. You'd select the 3 bits on the schematic and generate a scenario. Then couple the transmission lines representing the routing for each bit, and then set up the track configuration in any way you like. You could even have coupling between layers if that's what you wanted. Then solve it, and then you can simulate with tracks coupled in that way.
Hello again. So what are the main things you tend to do in the front end? Well, the first thing is you organise. The second important thing we did in the front end is to extract scenarios and simulate. And when we get to PCB design and put physical tracks in and so on, the simulation facilities and that extraction are exactly the same. And because they're exactly the same, they're easy to compare. And you can even share that kind of data from one design to another. So I look forward to seeing you again in physical design.